Hi everybody, welcome back to my YouTube video. Today I'm Yongking Bear. Today is another day of LeetCode practice and I face another challenge today which is about using big O notation of 1 in space complexity while traversing down in order traversal. As previously, I always learned that traversing in order traversal, we either use stack or it's also called depth first search as well. So we either use stack or we also can use recursion. But yeah, if stack and recursion, both of them will need like beyond notation of n space because we need to put n and nodes into the stack, and also recursion we need to keep track of all the recursive into like keep track the function and also the value and everything. It's very memory how to say intensive for actually recursion. So what is using big annotation of 1 to traverse down the what is it called, the binary tree, and I have to search for it. And in the LeetCode solution, a lot of people actually mention about Morris Tree. So yes, what is Morris Tree? I have no idea. I have to be frank, I have no idea. So it mentioned Morris Tree is the one that we use big notation of 1 for space complexity. And this video is the video that I will explain to myself how this code works. Okay, for example, starting with this simple binary tree, and it will start with the current equals root, which means this is our current. And if current left is none, which is not, so I will just skip this first and go to else, because current.left is not none, will be here. And it will put the left as the pre, I think it probably meant previous or something. So if pre.right is not none, and also pre.right is not current, it will continue traverse down. I mean, it will go like pre equals pre.right means it will go down. The pre will point to the next one, which is here. It will try to find the rightmost node of the left branch, and it will break the while loop when there's none in the right. So because the pre-write is currently none. So the pre-write, it will actually connect it to the current. And where is the current? The current is 8. So like this. The current is 8. So, and it will move the current cursor, the current pointer to the left, current dot left. Yeah. So it result in the next one, which is like this. So how does this, yes, so currently we are at B. B is the current because current.left is still not none. So we'll repeat the same thing by finding the most right node of the left branch, which is only D. There's nothing in the right anymore. So it will actually, again, connect it to the current. So it will connect it to the current and it result in this tree. And you notice that there's actually two like dotted like the dotted notes here. Why is it there? Because when we set like the pre.right equals current and current.left, we didn't actually cut off any ties, so it is still exists. Like the A.left is still to B, and the B.D is still, I mean the B.left is still to D, and it's sort of like forming a loop. Like D will point to B, B will point back to D, and for this one as well, like E will point to A, and A will go back to B. E is sort of like a loop. It's sort of like a loop here, and it's important for the next part, which I'm gonna explain right now. So we start with like current.left is none. because D do not have any left, so it will read the current value and it will move its pointer current to the right side. And now we're at this part where we're at the B. So the B, right side of the B is D. The right side of the B is D. No, yeah, the left side of the B is D, sorry. The left side of the B is D, so this is the pre, while pre.right is not none, and pre.right is not equals current. But actually, if you notice, the right side of the D is B, but it is equals current. It is equals current, so it won't be traversing. It will break this while loop. So once it breaks this while loop, we know that pre.right is not none because the right of D is B. The right of D is B, so it will go to this else statement. So this is the magic happens that I noticed. Yeah, why it mentioned is called the restore the tree structure is because of this part. Pre.right equals none. Pre.right equals none means that the D right is none. The D right is none means what? This part. This part is cut off. So it will actually restore the tree once we see at this part. I mean, yeah, it actually restore it because it cut off the link to the right side. So there's no more loop. And it will read the B, the current, because the current is B, and it will read the B, and it will move to the right side. Yeah. So it will read the B, and the current pointer will move to the right. So another place again. So for this, for A, it does the same as well, because it will go to the rightmost node, and the rightmost node of the right side, the right of the E is A, and it will actually cut off all this link because pre.right equals none. So it will cut off here. And yes, we got our original tree structure back. We actually restored the tree structure. And we continue down to C. And because it's like we're sort of like repeating because this is a while loop. So I'll repeat the same thing because the left side of C, there's something. So it will find the rightmost node, which it doesn't have, and it will move that how to say move, I mean you add the pointer of F to C. Yeah. And then to the next slide. So it became like this. It become like this because because that's left something. So it's sort of like moving all the left part into the right side. All the left part is moved to the right side, and you sort of like just reading down like a ladder down to the like down the ladder. And about restoring is just because there's a loop and you just cut off the loop once you found it. And yeah, that's sort of settle it. Yeah. So in the end, the time complexity at maximum, I think, is 2n, which is still simplified as n. Why? Because, yeah, you might be reading like D twice, and you'll be reading BDE twice, and you'll be reading F twice. So at maximum, it will be 2n, but it simplifies to n. And because we didn't really use any extra like data structure for this traversal, so the space complexity is n. Okay, I hope my explanation explains well about this special part, which I didn't get it until I tried to explain it myself, and it just become like a light bulb, and I suddenly understand, oh, because of this part, pre.right is none. It just cut off the link and it just restored the tree. Yeah. So thank you very much for listening. Until next time, bye.